Hello, everybody. Welcome to today's current seminar. Today we have one speaker, one talk. Our speaker is Dr. Sungbin Lim. He will be giving a talk on the score-based diffusion model in Hilbert spaces. Sungbin Lim is currently an assistant professor at the Department of Statistics at Korea University. He earned a PhD in mathematics from Korea University in 2016 under the supervision of Professor Kang Han Kim, and transitioned to the private sector as a senior AI scientist until 2019, and returned to academia in 2020. During his doctoral studies, he focused primarily on research in stochastic partial differential equations and diffusion theory. Since then, he has developed a keen interest in probabilistic machine learning, including deep generative modeling. He is also collaborating with LG AI Research on AI for Science projects. With that short introduction, the floor is yours and you can start your presentation.
Okay, thank you very much for inviting me for this wonderful French seminar. And actually, I have to apologize in advance that I cannot turn the speakers loud. So it's a local time, 1 a.m. So if you have any questions, please leave them in the chat. Then I will answer your question after the presentation. Okay, so today's presentation is on the following paper presented at the NeurIPS last year. So this is a joint work with my students, Sungbin and Taehyun, and Sungho, and Professor Kang Lee, and Professor Sungjun Choi. Oh, and also my student, Taehyun. Okay, so this figure shows the advances of generative models over the past 10 years. And even in 2014, the generative model was only capable of drawing the low quality images. But now we can synthesize the high resolution images. And furthermore, today's generative models can create images based on the text prompts that match the user's queries. So you can see that this type of generation process is called conditional generation task. And one can say that this kind of generative AI technologies such as DALL-E and Step Diffusion, so actually they have laid the leap that allows them to have the commercial value today. And now it is possible to generate images without any problems. So the next step is to generate a sequence of the image frames, which is called videos. So this video is a technology called Sora, released by OpenAI earlier this year. And like DALL-E, which we looked at previously, the Sora creates videos based on the text prompt according to the user's request. So the training method of Sora has not been fully disclosed, but it is based on the diffusion model, which we'll be going to introduce today. Okay, so the text-to-image or text-to-video tech is the technology that generated data in a two-dimensional pixel space. Okay, then is it possible to create the emotion of movie characters or robot in a three-dimensional space? Well, unlike the image domain, generating motion within a three-dimensional space requires some kind of restricted physical and geometric constraints. So it makes it much more difficult than a video generation. So this technology in this video is Flame, jointly developed by the research team at Korea University and the Kakao Brain in South Korea. So this tech Flame receives the text prompt and can generate or edit the motion of the characters in a three-dimensional space, considering the physical constraints of the body. Okay, so let me introduce my research motivation briefly. So as you can see in the previous slide, the score-based diffusion models have shown the many successes in the various domains. And especially in iClear 2021, Song proposes a framework of the continuous time score-based generative models that uses stochastic differential equations in the finite dimensional Euclidean space. And recently, there has been an active studies on the score-based diffusion models, such as generating a functional data. or replacing a drift coefficient with deterministic image transformation, which cannot be covered by the song's original SD framework in the finite dimensional space. Okay, so let me show you why this is. Okay, so the idea of the diffusion model is training a generative model that learns a stochastic process, or you can understand it as a random walk, moving from the noise space to the data space by gradually adding noise to the data point and training how to denoise it. And such ideas can substitute the blurring instead of adding noise to degrade the image. So in this case, the generative model can learn a different stochastic process, heading from a specific prior space to the data space instead of the noisy space. And this approach has already been introduced in a discrete time model in the inverse heat dissipation and the blurring diffusion, which is present at the last year ICLEAR conference. So then can we interpret these diffusion models in the SD framework in the Euclidean space? Well, unfortunately, these diffusion models use the differential operator in the drifted term, which means that it does include the Laplacian operator. So the corresponding equation is expressed as a stochastic PDE, which is not a stochastic linear differential equation. Therefore, it cannot be covered by the SD framework in the finite dimensional space. So motivated by this problem, we propose a unified framework for the continuous time scope-based generative modeling by using the well-established theory of stochastic evolution equations in the Hilbert spaces. Okay, so before introducing our research, I would like to briefly cover the basic contents of the score-based diffusion model in the Euclidean space first. Okay, the principle of the generative model is to learn the model distribution from the data observed from the unknown distribution. And our goal is to estimate the parameters of the model distribution based on the data. So once the model distribution, the training is complete, then we can perform the generation task. So we can actually do the generation task through the sampling from the model distribution. So therefore, the core principle of the learning in the generative models is to make the data distribution and the model distribution as similar as possible. So if the model distribution learned by the generative model is similar to the actual data distribution, then the data generated by sampling will also have a pattern similar to the actual data. And it'll be very difficult to distinguish from the actual data when a person observed it. So depending on how to form and use this model distribution, the learning methodology of the generative model will also change. So today, a wide variety of generative models have been studied, like generative address network, or a variational Tinker is very famous in history. But unlike generative address networks, school-based generative models and diffusion models belong to the methodologies that perform the density modeling explicitly under the maximum likelihood principle. Okay, so then what is scope function? The scope function refers to a vector field, which is defined by the gradient of the data density with respect to the variables. So as you can see in this picture, the data is observed from the mixture of two Gaussian distributions. And when drawing the scope function, a vector field towards the mode of the two Gaussian distributions. So in other words, the scope function flows towards the areas with a higher density on the support when the distribution is defined. Okay, so then why we use the scope function? Okay, when compared to the density modeling, the scope function modeling does not have to consider the normalization of the density. So this aspect indicates that the score matching takes the advantage of the energy-based method because the numerical integration for high-dimensional data is very difficult. And even if you don't know the exact density function, it becomes possible to sample from the data distribution through the MSIMS methodologies like a Sungbin equation. So since we know this co-function, okay, so theoretically, the marginal densities of the stochastic differential equation solution obtained through the Langevin dynamics converge to the data density. And due to these facts and the maximum likelihood principle, the score-based generative models have advantage in the high fidelity and diversity. However, in order to guarantee the high fidelity performance, the number of SDE steps must increase, which results in the slower generation. However, according to the recent research, and these advantages have been can be overcome by using some kind of the OD-based sampling. Okay, this is not today's topic, so I'm going to pass this later. So, okay, as you can see in the previous slide, the Langevin stochastic differential equation is based on the invert measure, which means that the drift term and diffusion coefficient of the SDE is time independent. Okay, but what if we consider a time-dependent coefficient in the drift terms and the diffusion coefficient in driving in the Wiener processes? Well, according to the recent diffusion model research, it has been revealed that the variance scheduler, that is the scheduler on the diffusion coefficient, it affects the performance of the generative model briefly. So then how can we, then with the theories work the same for the diffusion process if they contain the time-dependent coefficients for score-based modeling? Well, the answer is yes. So this theory is based on the time reversal theory of the diffusion processes. So more precisely, we can generate samples from the data distribution by running the reverse diffusion process, which contains the score function in the drift term. So in summary, by creating a trajectory between the data distribution and the noise distribution through a forward stochastic differential equation, we can design a reverse SDE heading from the noise distribution to the data distribution through the score function using the time reversal theory. So the goal of the score-based generative model is the training our score model to match the score function. Okay? So the name refers to the methodology of modeling the score function from the data. So which means that we are going to train our score model to approximate the score function based on the data, which has a foundation on the time reversal of the stochastic differential equation theory. Then how can you design a training objective function for the score modeling? Well, indeed, we don't know the true score function because it requires the information of the target data distribution, but we don't know what is the target density, right? Then how can you train the score model in our case? Well, fortunately, we can train the score model by using the conditional score function for given data instead of the true score function. So since we are using the forward stochastic differential equation to obtain x given p, note that the conditional density can be explicitly computed if we use a specific kind of the forward SDE, such as kind of the linear form of the SDE. So we can actually write the expressive formula for computing the conditional score function in the second objective function, which means that we can actually use this conditional score function as a target to train our score model. Okay, so the proof is actually based on the Fubini theorem and the integration by parts formula. Well, if you observe the proof carefully, the gradient vector of the log density is actually replaced by the gradient of the log conditional density, the gradient of the logarithm of the conditional density, because we can actually interchange the computation order between the integration and the inner product. And I'd like to remark that such interchange between the integration and inner product is also valid in the sense of the Bochner integral, if we consider the integration in the Hilbert space, because the inner product is a linear operator, and the Bochner integral can also interchange the order between the linear operator and the integration. So actually, this proof is also valid in the Hilbert space theory, if we can replace this co-function appropriately. Well, in the later, we are going to introduce the score operator instead of the score function in the Hilbert space theory. And if we use the score operator instead of the score function in this proof, actually, you can actually check that based on the interchange between the inner product and the linear, the inner product and the integration. Actually, this foundation of the theory of the score-based degenerate model also works for Hilbert space valued theory. So therefore, the two objective functions are identical, except for the addition of the constant term with respect to the parameter theta of the score-based model. Okay, so the proof is done because these two terms are equivalent up to the addition of the constant, which means that if we optimize the score function with respect to the theta, we actually train our score-based model using the gradient method, which means that this constant term can be ignorant in the optimization procedure. So these two objective functions can reach the same optimal parameters with respect to the theta. And one more thing that you need to know is that training the score model and the diffusion model is equivalent because their targets are identical. So the only difference is that the diffusion model use the discrete time the Markov chain, but our score-based approach is using the continuous time the stochastic differential equation. So in this presentation, we are going to use the score modeling and diffusion modeling as an equivalent terminologies in this presentation. Well, in practice, actually, the diffusion model refers to the discrete time modeling, whereas the score model actually refers to the continuous time modeling. But in this presentation, we are going to use the same terminologies, okay? And so this is the algorithm for the score-based model. So after we train the score model by using this training model, then we can actually plug this as score model as theta in the reverse SDE. Then we can actually solve this reverse SDE using like Euler-Maruyama solution for a solver to run this as reverse SDE for the sampling. And so this training algorithm and sampling algorithm does work. We are going to use this algorithm as well in the Hilbert space theory. So, well, these algorithms are identical in the infinite dimensional cases. Okay, so now we are ready to introduce my work as score-based diffusion models in the Hilbert spaces. When you have to deal with stochastic equations in the Hilbert space, we need to prepare additional setting to deal with the infinite dimensional spaces. So we assume the negative and symmetric and self-adjoint and finite trace covariance operator with an eigensystem. So then we can define the Cameron-Martin space H lambda, which is another Hilbert space. And by using this eigensystem, we can actually define the lambda Wiener process in the Hilbert space with a series representation. Well, you can understand the difference between the finite dimensional Euclidean space and L2 space with a reproducing kernel K lambda function. So that the covariance operator is defined as integral using the kernel function. So in this case, the reproducing kernel Hilbert space, the RKHS, is definitely different from the L2 space. So you can see the difference between the finite dimensional Euclidean space, which is also the Hilbert space. In this case, the H lambda, which means the Cameron-Martin space is identical to the Hilbert space, but in infinite dimensional space, they are not the same at all. And this is the reason that we have to consider the finite trace operator in here. Okay, so in this setting, the SD theories in Hilbert spaces are well established, actually. Well, I'd like to mention that some researchers actually they actually try to build diffusion models in the Hilbert space or infinite dimensional space without considering the time-dependent operators because they are using semi-group approaches. So actually, they are based on the Langevin dynamics. However, as I already mentioned before, the variance scheduling is a key component for the good performance in the generation test, especially for training the diffusion models. So, so therefore, we have to consider the time-dependent operators as well. And so we can actually include the stochastic heat equation with spatial time the white noise in this case. So a time and also the time reversal theory for Hilbert space valid equations are already introduced in the 1990 by Dalecki and Bellascalia in the 1990 papers. So they already introduced this time reversal theory for the stochastic evolution equations in the Hilbert spaces. And they have a big difference between the previous semi-group approach, which cannot deal with the time-dependent operators. So our approach is based on these theories, and which can deal with the time-dependent operators. So as we said already, the contrary to the other approaches using semi-group theory, well, our approach is grounded in the homograph operators with functional derivatives. So as you can see in this slide, we actually define the homograph operator using the Gato derivatives. And this is also well studied in the variational approach to the stochastic evolution equations. And actually our approach is able to deal with the time-dependent operators because the homograph operators can include the time-dependent operator, as you can see here. And in fact, this approach can generalize the original frame proposed by Song's paper in the Euclidean space. So if you remember the previous slides, actually they contain the time-dependent coefficient in the drift terms and the diffusion coefficients. And because our equations can include the time-dependent operators, actually our Hilbert space framework can include the original SD framework in the finite dimensional cases. And in this paper, we explicitly derive a time reversal formula in the Hilbert space so that the drift terms and diffusion terms of forward and reverse stochastic evolution equations are connected through the score operator, which is defined by the GT operator in the stochastic integral, and the vector logarithmic derivative term, the rho ut h lambda here. So here the ut means the marginal distribution of the stochastic, the forward SDE in this case. And h lambda denotes the Cameron-Martin space, which we already defined before, okay? So this rho h lambda mu t is the key to understand what is the score operator in our theory. And this is actually generalized the term of the gradient of the robot density in this, which is defined for a support function. So this time reverse formula generalized the time reverse formula in the finite dimensional space because the vector logarithmic derivative recurves the gradient of the robot density. If you remember the formula in the score-based, the objective function of the score-based modeling, then actually we can replace this we can actually replace the score function by this score operator. And we can actually, in this case, we have to use the norm with the Hilbert space norm in this objective function. Okay, so for detail of this Kolmogorov operator and the formula, please see our paper. Okay. So, so in summary, we are able to derive a time reverse formula in the Hilbert space, and we can also compute the score operators explicitly for training generative models. And consequently, our framework integrates with the zones frameworks in the Hilbert spaces successfully. So now we can propose the new class of the generative models we call the Hilbert diffusion models that build a bridge between the score-based generative models and the stochastic PDEs, which can actually explain about how can those inverse heat dissipation model can work, as we already introduced in using the blotting operators. Okay, so in our paper, we proposed the two types of the score-based generative models based on the first one is the SDE in infinite dimensions, okay, which is called HDM SDE. And another one is the parabolic stochastic partial differential equation, which is based on the which is actually based on the parabolic the stochastic heat equation. Okay, and these are called HDM SPDE. Okay, which is the second version, as you can see in the below. Okay. So as you can see that HDM SDE, which is using the SDE in infinite dimensions, is designed for the functional generation. And because we want to deal with the functional generation in the function spaces, this is actually a natural choice for using the SDE in the infinite dimensions. And HDM stochastic PD is designed for the image generation in the finite dimensional space. So in this case, we are going to use the blurring operator. So we are going to use the Laplacian operator instead to implement the blurring operator. So by using those blurring operators and the noising process, both we are going to use the blurring operator and the noising processes. Then actually that equation is can be represented by the stochastic PDE. So because we actually proposed the stochastic differential equation in the Hilbert spaces, and since we are going to use those differential operator as the diffusion, the drift terms as a BT here, we can actually contain those. We can actually deal with those SPD. HDM SPDE as our special case in the Hilbert diffusion models. Okay, so but in this case, we the previously diffusion models actually they used a unit for training the score model, but in our case we cannot use the unit naively because we have to deal with the operator case because we have to train the score. We have to train our model to match the score operators. So we have to propose some kind of the operator value, the function valued neural networks. So to train the score model in our research, we propose a time conditioned Fourier neural operator. So we modified the original Fourier neural operator by adding a positional embedding to derive the time variable and the linear layer to embed the time variables. Okay. And the spatial variable x first passes through the lifting layer, and it increases each dimension to match the lifting channels. Then the embedded time variable undergoes the linear layer to adjust its dimensions to match the lifted spatial variable and is pointwisely added. So the Fourier layer takes the input and applies the fast Fourier transform to transform it to the frequency space, followed by the spectral convolution. Okay, so now let us show the experimental result. Okay, this shows the functional generation text using the HDM SDE, which use the SDE in the infinite dimension space. So we apply the HDM SDE to functional generation tests, which use the different grid points in the training and the inference phase. So in this task, we use a different kind of the function data, okay? So in the training phase, we fix the grid point in the unit, which use the uniform grid in here. But for the sampling, we are not using the same grid point which used in the training. In fact, we use the grid point which is uniform, the sample from the interval uniformly, okay? Which means we use the uniform distribution for sampling the test grid point here. So therefore, this is not a trivial task, since the model must meet the unseen grid point when generating functional samples. Compared to the other method, the proposed method generates the proper functional samples, which are close to the original data test. So as you can see, the proposed method can generate much more proper functional samples than other functional diffusion models. Okay. Okay, so the previous experiment shows the one-dimensional functional generation, but actually we can think about the much more difficult task like motion generation, which is a kind of the 3D, which is the function generation in the 3D dimensional space. So we also applied a Hilbert diffusion model to the motion generation task. Okay, so since this task requires the sampling, the smooth and the physically valid motions, okay, it is actually necessary to consider the differentiable function space as a Hilbert space. For example, you can actually sample from the Sobolev space. But in this case, we actually choose the typical example as a function, the differentiable function space as the RKHS. So we consider the forward and the reverse SDEs with the winner processes in the RKHS. So as a result, the proposed HDM SDE can generate smoother and more valid motions, which are statistically close to the original motion data in terms of the maximum mean discrepancy compared to the just a DDPM case. Okay. Okay, so now we are going to show some research in the image generation task. And as we already mentioned before, our work built a bridge between the inverse heat dissipation, IHDM, and the school-based gen models using a parabolic stochastic PDE. Well, since our method can utilize the various scheduling, we can improve the performance of IHDM in terms of the FID score. Okay? And you can also observe that the connection between IHDM and our proposed method, HDM SPDE, so they actually share the same prior space, as you can see in the right-hand side, which is very different from the Gaussian noisy spaces. Okay, so which means that the IHDM and the HDM actually they use the same prior spaces, whereas the HDM can generate much more the high quality samples than the IHDM because we can actually utilize the various scheduling. Okay, so let me give you a quiz. So can you guess which pictures are generated by our HDM SPDE? Can you guess it? Okay. Okay, these are the generated images. Okay. Okay, so, well, we actually blur the original image, these dog images, and pass it to our generative model. Very importantly, we don't actually need to fine tune or we don't have to train our model additionally because our model, HDM SPD, can learn how to generate images samples from the blood image. So remember that our HDM SPD has the same prior space with the inverse heat dissipation model, IHDM, which means that we can start to read this blood image as a prior space. So we don't have to train our model additionally, but we can just sample, we can actually just generate images from these blood image samples. And you can actually observe that our image is very high qualities compared to the previous method. And very interestingly, we can actually generate our images based on not only for the blood image, but we can actually generate images from the pixelated space, not only from the blood one. So these are low part images generated from the pixelated images from which is pixelated from the cat images. And as you can see that in this image, in this experiment too, we don't have to train our model additionally, but we can just start with this pixelated image to generate this low part image. Okay, how about this one? Can you imagine the original animal in this image? Well, I think that, well, this problem might be easier than before. Yeah, the answer is a cat. So as you can see that the proposed method can recover the original image from the master image without any additional training. Okay. Well, I would like to mention that such generation is impossible for the original DDPM or the previous method introduced by the Song. Using the score-based generative model in the finite dimensional cases. Well, so starting from the degraded images, as you can see that the DDPM actually generates samples that do not preserve the prior information, such as color or morphologies from the original image. Okay, as you can see that the color distribution actually disappears, and their actually qualities are not as good as their quality is not as good as before. However, the proposed method can generate the samples preserving the prior information like colors or actually they can preserve the color informations and they can actually generate the samples from the pixelated images better than the DDPM cases. And this is another interesting research of the HDM SPDE. So we can actually transform images from the different domain, like MNIST domain. Okay, so as you can see that our model, okay, so we actually take the blood operation from the MNIST data to get the blood images. Then starting from this image, we can actually sample the animal image from this MNIST part, the blood images, which is actually started from the MNIST data set. And the right-hand side, we actually transform the images from the human face images to the AFHQ, the animal face images like this, starting with the pixelated images from the human face images. And these sampling, this generation is possible. I would like to mention that this generation was possible without the additional training without any additional training. Yeah. So actually, this means that we can say the Hilbert diffusion model can include the operations other than just the blurring. So we can actually include the masking or pixelating as you can see before. So therefore, we can say the diffusion model in Hilbert space can explain that how core diffusion works, which is present in the 2023. Okay, so this would be a final slide in this presentation. So I'd like to mention this additionally. So recently, we actually also released a new study dealing with the diffusion glitch in the function space, which is the theory on the Hilbert spaces, an extension of the research we introduced it today. Okay, so I really greatly appreciate your interest and thank you very much for your attention. Okay, so I would like to check the question from the chatting. Okay. Okay, so Lulu asked the question, could you be more specific why we need infinite dimensional SD here, for example? Oh, On page 29, if you're in the training of FNO, the input and output dimension are fixed. So we can still use five-dimensional unit. Is this right? Okay, so you're asking the question about the 3/8. Oh, you mean the experiment on this page, right? Yeah. So yeah, the resolution is changed in this case, and so we actually sampled the grid point from the training and the test here, but actually the training and test data are sampled differently, which means that we cannot observe the same grid point in the test phase as a training data grid point here. And of course, in the image generation task, we can actually consider the different resolution case for the image generation task. So for actually, I didn't include the experiment here, but there's another, oh, sorry, I didn't include the experiment here, but there is an experiment about the super resolution in this case. Well, theoretically, those functional generation can be applied to the the resolution-free sampling here, which means that actually it does require something kind of the neural operators cases. Okay, and that's the reason that why we use the neural operator. And of course, we can still use the fine-dimensional UNet for image generation task. And actually, in our experiment for the image generation, we actually used the UNet also. And in this experiment, actually, we actually use the UNet in these cases. But if you want to apply the neural operator for the super resolution task, or if you want to do it resolution-free generation, you can also use the neural operator for training the school model. Okay, so I think I hope this answer will be enough, sufficient for your question. Okay, so if you have any other question, please leave the question to the chatting, then I will answer the question.
Thank you so much for your great talk. Do we have any question for the speaker? You can put the question in the chat. Did you check on the question in the chat from Lulu?
Oh yeah, I answered the question. And
Yeah, and another question. Is it possible to take derivative and with respect to the input for the generated functions?
with respect to the input for the generated function. Oh yeah, very good question. Yeah, it is possible because actually, in this case, for example, if we generate the functional from the functions using this reverse SDE, then we can actually obtain the coefficient about the basis functions. Okay, so we have the basis functions for sampling the functionals, which means that so let me explain this more precisely. So as we already introduced here, so for example, let's deal with the RKH's case, that we have a certain kind of an origin system here, which means that we have a basis function. Those basis function is actually differentiable. And we have and through the sampling, we actually obtain the coefficient for those basis functions, which means that we can actually take the derivative with respect to these functions. So we can actually say, that it is possible to take a derivative with respect to those generated functions.
Thank you. Do we have any other questions?
I have a question.
Can you put your
Should I write
question
it
in the chat?
Yeah, okay.
I'm
Thank
sorry,
you.
I cannot turn on the speaker loud, so I'm really sorry for that. Yeah. I'm really sorry for that. I actually I put my baby into the bed. So yeah.
Since the score operator satisfies a SDE, have you looked into the following work to estimate the score operator? Can you open the link? There's a link there.
Let me first of all.
It is the Neural Stochastic PDEs paper, resolution invariant learning of continuous spatiotemporal dynamics.
Okay, let me check this first. Oh, I remember this paper before, and yeah, this paper is also proposed the training the score operator in this case, and actually actually our theory has a very similar is very similar to this kind of the previous works. But I remember that the time reversal theory of the school-based, our approach is actually based on school-based generative models, which requires about the time reversal theory in the SDE, in the Hilbert spaces. But in this case, but in this paper, actually, it is far from the school-based generative modeling, which does not use the time reversal theory in this case. So yeah, and this paper and our paper does have the common thing that actually we have a common thing is that this is actually can deal with the stochastic PDE, and our paper can also deal with the stochastic PDE, but they actually can, but and it is also possible that this work can deal with generating the resolution-free images, and and this can be same in our case also, but our model is based on is targeting the proposing the school-based generative modeling using the time reversal theory, and actually that is I think that is the difference between this work and our work.
Thank you so much. Do we have any other questions? I think there is no more questions, so it's time to close the session. Thank you so much for your great talk and for your time. Thank you everybody for joining us